Good morning, friends. I hope you all are doing good. So, as per our last video connection, let us start with the unit number 2 from the subject called Multimedia Communication Technique, final year Electronics and Telecommunication from Solapur University, Solapur. Now, as the title goes, for unit number 2, color standard and the digital video. Now let us go through one of the major contents like which we will be covering in this particular chapter. Those will be television transmitter and receiver, color television transmitter as well as receiver. So firstly we'll go ahead with the basic monochrome television transmitter and receiver, and then color television transmitter and receiver. Then we go ahead with a concept called as frequency interleaving. Then there are three standard for color television transmission. Those are NTSC, encoder, decoder, PAL, encoder and decoder, and CCAM, encoder and decoder. So basically three color television standard, NTSC, PAL and CCAM, which is mostly preferred all across the globe. Then there will be comparison between NTSC, PAL and CCAM. And lastly, we'll study one more concept called as color bursts. So these are the major contents which frequently asked in the examination and the major content from chapter number 2. Now, the image which is there in front of you is just going to give you a brief introduction how basically a television system works. Now, as the name indicate, television, it's like vision from a long distance. So basically we start with shooting one particular scenario at a distance or a remote place with the help of two things: digital camera followed by a microphone. So audio and image both we will be capturing, then it will be amplified, and then the processing took place where we go for amplification followed by sound as well as picture modulation. Then there will be a circuit by which we will be combining both the signal, that is sound as well as audio, that is sound that is audio as well as video. Then there will be power amplification, and then it will be feed to an antenna, so where the signal will be converted into electrical pulses or electromagnetic transmission we can go ahead with. Then those signal travel in air, and at the receiver side, as this is a broadband communication, broadcast communication, so from one particular antenna the signal will be transmitted, and there will be several antennas by which the signal will be received. Then there will be an receiving antenna here, to which a tuner circuit will be there. So a tuner circuit based on which frequency, rather which channel we need to tune, so it will tune it accordingly, and then we will get that subscription of that particular channel. Then there will be a block called as video detector, where audio and video will be separated out, and then the demodulation of the sound and picture, that is audio and video, will be demodulated, which is actually modulated at the transmitter side. So reverse process will took place here, and then audio will be processed through a loudspeaker, and video will be processed to a television set, where the RGB signal, if color television is there or if monochrome is there, then only a video signal will be given to a television set, where depending upon the strength of the signal will get the illumination on the phosphor screen. So this is how all in all in color television or black and white television transmitter and receiver system, how basically how it works. So this is just a very general block diagram how it works. So let us go through in detail one by one. So let us go ahead with the television transmitter first. So as we have seen that whenever we transmit a signal, what we do is we capture the audio signal as well as the video signal. Then both will be combined as we have seen in the previous block diagram, and then it will be amplified and transmitted via an antenna. But in that particular communication channel, in that particular communication link, what are the steps that it follow? Let us go through it one by one. As at the receiving side, when we capture the video signal, you actuate the light, At the microphone you capture the sound variations, that is pressure variations. Then this light information will be converted into an electrical signal with the help of television camera. Then it will be amplified, and meanwhile there is a block called as scanning and synchronizing circuit. So it will help you to have synchronization between the, like as we have seen in the first chapter, that whenever we capture a video, that exactly means we are capturing an image, and while capturing the image we follow a process called as scanning. So where one image will be divided into number of lines, and we actually capture the information line by line. So in order to have a proper synchronization between the transmitter side and the receiving side, like whenever one line information is completed, then electron beam has to move from right to left so that it can get started with the next line. So in order to maintain this synchronization between the transmitter and receiver, we need this scanning and synchronization circuit. So where we will be feeding certain pulses, with the help of which it will be very easier at the receiving side to detect or to control the electric beam, in order to control it from left to right and then from top to bottom. So this is very important block called as a scanning and synchronization circuit. So we connect that with the video amplifier, and then we combiningly go ahead with the modulation. Now here and video signal is there, so you go for an amplitude modulated video signal. And obviously whenever we say modulation is there, we need to go for crystal oscillator, RF amplifier, and then amplifier. With the help of that we modulate the audio, this video signal. Then similarly, parallelly, whenever video is been captured, similarly audio signal is also get captured, and similar kind of process is followed, that is capturing of the audio signal followed by amplification followed by the modulation, with only change that whenever we go for modulation, we prefer frequency modulation for audio signal and amplitude modulation for video signal. So once the modulation has been done, then both the signals will be given to an combining network here. So a combining network is a circuit where the audio signal modulated the audio signal modulated and video signal modulated will be combined in a single signal, and then after amplification it will be feed to a transmitter antenna, where it will be converted into electrical pulses or electromagnetic waves. And this is how an monochrome television transmitter works. Then what happened at the receiving end is, in detail if we see, there will be a receiving antenna which will be driven by an RF tuner. So based on what kind of channel that we wish to see, we tune to that particular channel with the help of RF tuner. Then there will be a common IF amplifier, so an intermediate frequency will be selected. See, because we need to deal with variety of channels, so there will be say hundreds of different amount of video signal channels available, but entire circuitry within the television set cannot change for each and every channel band. So what we rather do is, the entire circuitry will operate at a single band of frequency only. So for that, whatever may be the channel input, so it will convert it into that intermediate frequency, and for that only we need this IF amplifiers. Then there will be a video detector circuit. As we have discussed earlier, video detector is the circuit where a video signal and audio signal will get separated out. So when audio signal gets separated out, it will be processed separately, where sound IF signal will be, intermediate frequency signal will be amplified, followed by demodulation of FM, and then after amplification it will be given to a loudspeaker. So where your audio signal, that is electrical signal, will be converted into the pressure variations with the help of loudspeaker, so that we can get whatever the sound signal that we have recorded at the remote location, we could exactly get the similar kind of sound signal at the output of a television receiver or television set. Then whatever the video signal that we have separated out, that amplified video signal will be given to a picture tube, where the intensity of the beam will be controlled by a certain DC source. But when that beam is passing through an electric heater, then it has to face two voltages at the cathode voltage as well as the focus voltage. So generally what we do is, that is cathode voltage as well as grid voltage. So generally what we do is, the video signal will be given to a cathode voltage, so that cathode supply is going to oppose a number of electrons that is passing out of an electron beam. So that in short, not to get confused, whatever number of electrons that get emitted from the heater at the picture tube, now how many of them are going to strike the phosphor screen? Like in short, if more number of electrons get passed through a heater and strike the phosphor screen, obviously brightness level will be very very high. And if less number of electron beam, or rather less number of electrons get passed from the heater and strike the phosphor screen, the brightness level will be low. So what a video signal does here is, once the video signal voltage is given to the cathode, then according to the variation of the video signal, according to the amplitude of the video signal, the cathode voltage will vary, and it will ensure that how many electrons should go and strike the phosphor screen. So in short, the number of electrons striking the phosphor screen will be controlled by the cathode voltage, which is nothing but the voltage given by the video amplifier. So your video signal which you have transmitted at the transmitter side of the television set is going to control the intensity of the light or illumination which at the phosphor screen. So in short, what you are going to see on the television will be totally controlled by the video signal that you have already captured at the receiving side. And then obviously whatever like here earlier we have seen that synchronization signal circuits are required, scanning and synchronization circuits are required, so that electron beam can move from left to right and right to left. So here we will give those pulses. This particular part here we call it as a deflection circuit, which ensure that the beam movement of the beam from left to right as well as from right to left. And this is how a television receiver, a normal basic television receiver, what diagram that I have shown here is a monochrome television receiver only. That is how it works. Now let us go ahead with the color television system here. Now when we talk about color television system, what difference that it has with the help of monochrome is, monochrome generally means a single dimensional signal where the video signal intensity varies, then accordingly the video signal intensity varies, that means the brightness of the scene get varied. So if the intensity is very very high, the brightness level will be high, and intensity is low, the brightness level will be low. And that is how the scene works. Like for example, monochrome television is nothing but image represented from white to black. So whatever in between gray shades are there the amplitude variations took place. Now if you want to represent this signal, you can represent with the help of a single signal only, where the amplitude variation gives you the variation in the intensity level. So monochrome television signal is only a single dimensional signal where only the brightness or intensity values varies. While if you go for color television, now there are n number of colors available, but what we do for color television system here is, every color is made up of 3 primary colors. So whatever color comes from the transmitter side, or whenever we capture the video, that there itself whatever color is there, convert that color into the different values of R, G and B. So a color television system is basically having 3-dimensional signals here. So that way color television has 3-dimensional inputs here. So obviously we need to deal with more and more number of signals here, because we have to solve the issue of compatibility as well. Now what do you understand by the compatibility? Compatibility means here, if a a person is having a black and white television at his household, and if entire world has switched back to color television system, so a person having black and white television set, in his television set there is a picture tube in which only one electron gun is there, and with the help of that one gun only he is to see the entire picture, the brightness values. But if entire world is running with the color television system, whatever signals transmitted or whatever the signal that is moving around will be having three dimensions, that is values for R, G and B. But a person having black and white television, if he receives these three signal, the television set will not operate, the television set will not run, or won't be able to show the picture on the television set. And that is the reason why we need to answer, or we need to tackle down the issue of compatibility. Similarly, reverse case also it happened, that if a person is having a color television set in which three electron beams will be there, or three electron guns will be there, one for red, green and one for blue, then this RGB picture tube, if the transmission through air it receives is a black and white, say for example, if old movies, if you look for, those movies are like pictured way back, so those are into black and white only. So those black and white television transmission signal will be having only one dimensional information. And if at color television set you have three guns, so where to, or to which gun you should feed that particular signal won't be justified, or your picture won't be visible properly. And that is the reason why you need to go ahead with the compatibility, which states that a monochrome or color, whatever may be the signal transmitted, and a monochrome or color, whatever may be the television set receiver is available, all the signals should be able to see on black and white as well as on color television. So in short, color signal must be visible on as well as on black and white TV, and black and white signal should also be visible on color as well as black and white television set. And that is what compatibility means. And in order to solve this compatibility issue, we need to go ahead with one more signal, which is called as luminance signal. What does this means? It means that we need to go ahead for color television transmission additional signal referred as luminance signal Y. A luminance signal Y is nothing but brightness information of a color signal. So in short, let me summarize this quickly. For a color television transmission, we will be dealing with four signals. That one is red, green and blue. Along with that, for keeping in mind of compatibility issue, we need to also transmit a signal called as a Y. So logically speaking, if number of signals has increased from in to color from 1 to 4, so obviously bandwidth requirement will be increased. But constraint here will be bandwidth cannot be increased. So whatever 7 megahertz of the bandwidth that we have for entire channel, in which modulated video signal is to be transmitted along with audio, the space given to us, or the bandwidth given to us, is only 7 megahertz for black and white, and same in that same bandwidth we need to fit the color television signal. And that is what additional compatibility consideration that we must go for. Now what do we do as a solution here is, for color television signal, for R, G and B signal, instead of transmitting these three signal, we go for deriving color difference signal out of R, G and B. That means from R, G and B plus Y, we generate three signals. Y is as it is. Secondly, we generate R minus Y and then B minus Y. So we were earlier having four signal, R, G, B and Y. Then from those four signal, in order to reduce number of signals, because if number of signals increases, obviously bandwidth increases. So what do we do here is, to reduce the bandwidth, we reduce number of signal. And how do we do it? From R, G and B, instead of transmitting these three signals separately, we transmit color difference signal of R minus Y and B minus Y. Obviously, along with that, we also transmit Y. Why we don't touch? Because if black and white television set is there, we need to provide the signal to that set, television as it is, so that color television signal could also be visible on black and white television set. Now I think I have made it clear that in order to reduce the bandwidth from R, G, B and Y, we come down to three signals, that is R minus Y, B minus Y and Y. Now we have signals which represent color information, those are R minus Y and B minus Y, and we have one signal that represent monochrome information, that is nothing but Y. But earlier we have seen, in order to transmit monochrome or brightness information, we already require a 7 megahertz of the bandwidth or 7 megahertz of the space we require. So for this additional color information, where do we fit the signal? And there come the concept in picture. We call it as a frequency interleaving. Now what do we do in frequency interleaving is, first we need to analyze, like if monochrome television is there, we require a higher bandwidth. Like for a monochrome video signal itself, we require 5 megahertz of the bandwidth. Now why do we do it? Because we can easily identify the differences between the shades of gray color, and that is why the resolution there has to be very high. And if resolution is going to be high, obviously the width requirement is also going to be high. Now if we are considering that for monochrome or for black and white television set we require higher bandwidth, then if you will go for color television signal, how much bandwidth we will require? So surprisingly here is, there are n number of colors. So if number of colors are more, our human eyes can easily identify the difference between the colors, so that we don't have to go for higher resolution for colors, because colors can be easily differentiated. And that is why if we go for combining the transmission of both these color signals, that is R minus Y and B minus Y, surprisingly we require a bandwidth of only 2.5 to 3 megahertz only. And that is the reason why what do we do here in frequency interleaving concept is, whatever the bandwidth required for color television signal is hardly in the range of 2 to 3 megahertz. So we ensure that this 2 to 3 megahertz signal will be interleaved between the color television, the black and white television signal bandwidth only. Now it is shown here in this particular diagram that this is how Y signal bandwidth look. Now for a monochrome transmission signal, for lower frequency signals, the amplitude levels will be very high. If we go for high frequency signal, the amplitude levels are comparatively very low. And that is why we get many empty spaces with low amplitude. And here you can see there are patches in between. Here between two frequency nodes there are few empty spaces available. So what do we do in frequency interleaving is, we ensure that whatever the empty spaces are available in monochrome television signal, whatever the empty spaces available, harmonics of the signal of monochrome television or luminance information, we ensure that our chrominance signal will be interleaved into that particular space. So here you can see easily, so whatever the harmonics values gaps are there, in those gaps only this chrominance signal or information will be interleaved or is been interleaved. So in short, frequency interleaving here means we have a bandwidth of 7 megahertz dedicatedly given for a monochrome signal, and then we have additional 2 to 3 megahertz of the bandwidth required for color television. So we don't add the bandwidth of color television plus the monochrome television. In short, we don't go for simple mathematics of 7 megahertz for black and white and then plus add 3 megahertz for the color, so that together 10 megahertz. We don't go for that. We don't have luxury for going for that, because already we have compatibility consideration where the bandwidth is the main limit. So bandwidth we cannot increase. So in short, we have bandwidth of 7 megahertz, and in that 7 megahertz only we have to transmit color as well as black and white. So what we do in frequency interleaving is, whatever space or whatever gaps are available in the monochrome, in those gaps only we start transmitting the color information. So whatever the gaps are available in the harmonics of the frequencies of monochrome, we add our color television signal. We ensure that generally at the higher frequency side, where amplitudes of monochrome signal are low, there we purposefully add this color television signal, so that it will not get mixed with the monochrome signal. And that way we go for frequency interleaving, where we save sufficient amount of bandwidth by combining color television within the monochrome television only. So that the third compatibility consideration, where a constraint was put on the bandwidth, we successfully able to fetch that for color television bandwidth requirement will not increase, and that is what we do in frequency interleaving. Okay, now let us go ahead with how the transmitter of television will change if we go for color television system. Like we have seen here the transmitter for black and white. Now let us see what will be the changes once we go for color television system here. Now the basic here we have a color camera. Earlier we used to have only one video signal output. Now we have here three video signals outputs here, that is R, G and B. Then there will be a matrix here. Now why this matrix is required? Because we mathematically operate on that particular signal of R, G and B, and ensure that from R, G and B value we will derive three signals. One is the signal Y, that is from color television we derive a luminance or brightness information of that color television, that is Y signal. And then we derive two more signal called as a color difference signal 1 and color difference signal 2. Now generally we got to study three color television standards here. So in this chapter only we will study those. One we call it as a NTSC color television standard, PAL color television standard, and lastly CCAM television standard. So all these three different standards require three different color difference signals. Like in case of NTSC we use I and Q, in case of PAL we use U and V, and in case of CCAM we use DR and DB. But all in all the difference, the signal on which they will be working is, we call it as a color difference signal for red and color difference signal for blue, that is R minus Y and B minus Y. Now once we derive these two color difference signal, we give it to a color encoder. Now color encoder here means it can be a PAL, it can be a NTSC, or it can be a CCAM color encoder. Once that color encoders is ready to deliver the output, and then expected output will be the chrominance signal C. So there will be only one signal, one chrominance signal available, which is combination of both R minus Y and B minus Y. Now in NTSC we will see it in very detail that how to two signals can is converted into a unique one signal only, which is referred as chrominance signal. Then uh, we need to transmit this color information also, and obviously when we go for transmission of color signal, we need a color subcarrier also, that is we require a color carrier also. So for luminance we have one carrier, so for color also we need to have one carrier. So here we have subcarrier generator. Now in order to save the power, we follow here a balance modulator, where a carrier at color the carrier on which this chrominance signal is mounted, which is referred as color subcarrier. We suppress this color subcarrier and then we go for transmission. So a color subcarrier is suppressed, so at the receiver side, in order to re-obtain this original color subcarrier with the same phase and frequency, we go for one more thing additional, and that also we will see in detail. We also go for deriving a signal called as a color burst signal. Here you can see here a gated pulse or color burst signal. Now this color burst signal is derived from the color subcarrier. So those color burst signals are nothing but 8 to 10 cycles of color subcarrier only. Now what additionally we have here, we have a luminance signal here, we have a chrominance signal here, we have a color burst signal here, and then we add all those signals in order to get this CCVS, that is nothing but color composite color vestigial sideband amplitude modulated signal. So here what we do is we go for, obviously we go for modulation signal, but now earlier we have seen in chapter number 1 the composite video signal, but here now we call it as a color composite video signal, where it will be a combination of monochrome, chrominance, color burst, and obviously a synchronization pulses. So all in all 4 signals are been added here, and combiningly those are called as a color composite video signal. Then obviously it will go ahead with modulation. Here also we use amplitude modulated with vestigial sideband. Then we go for a combining circuit here, where the audio signal is here you can see the audio signal is frequency modulated, and then by combining them after amplification we pass it on to a antenna, and then that signal will be transmitted through to the air, and that is how a color television transmitter works. Now you have easily identified the difference between the transmitter for black and white and color. In black and white we only deal with one signal, so one signal, that is one dimensional signal of video signal. For luminance, additional to that we send synchronization pulses, and that's it. That all together we call it as a composite video signal. But color composite video signal is having 4 kinds of different signal. One, luminance, that is brightness information, then a chrominance, that is nothing but color information, then color burst, which is 8 to 10 cycle of color subcarrier, and then the synchronization pulses. So here the load is more, so obviously the transmitter here is complicated than that of a monochrome television set. Then next here is a color television receiver. Now earlier receiver we have seen, where we have seen only antenna followed by a tuner followed by an IF stage, then a video detector where audio and video will be separated out, a demodulator, and then the output. But here you can see there will be a huge section here, because we need to derive or we need to separate out the values of luminance, values of chrominance, then the audio signal, then the synchronization, and then we need to process with the signal. So color television receiver, as it looks a bit complicated. Now let us see it one by one. Now here we have an pickup antenna. Obviously every television set is coupled with an antenna, So obviously a tuner circuit is required, because as per the channel we need to prefer, channel we need to select, a tuner circuit will tune to that particular channel, a frequency will be selected, and the output will be telecasted. Then there will be an IF stage, same working, because here also the entire television circuitry at the receiving end will not be working for different frequencies for different channels. It will be working for a single set of frequency for all the channels. So here also it require an IF stage. Then once the video signal is detected and amplification is done, we need to go ahead here is with this important block called as a color demodulator. So whatever modulation that we have done at the transmitter side, let it be NTSC, PAL or CCAM, similarly a reverse process would took place at the receiver. That means, so how because at the receiver we will be getting a that is a composite color signal which is having 4 components. So all those 4 components need to separate it out, like chrominance, luminance, sound, and chrominance, luminance, then synchronization signal, and as well as color burst need to be separated out. Then each of that component need to give pass it on to a different section, and then it will be processed separately. Similarly here we have a color decoder where a chrominance signal will be separated out, and it will be given to a reverse matrix from which a chrominance signal will be converted into an R minus Y, G minus Y and B minus Y signal, from which we will derive the value of R, G, which are given to the separate picture tubes or separate electron guns, so that they can control the every pixel dot which is available on the phosphor screen from red, green as well as blue. Then from here, whatever the synchronization pulses were there, those synchronization pulses will be separated out and given to horizontal as well as vertical deflection circuit. Audio signal here will be separated out, and then the demodulation amplification will took place, and then it will be passed through a loudspeaker, and that is how a color television receiver will function. Now I think enough of this will be for today. So you just revise this, go through the video again, and just feel free to call me if you have any kind of doubt. So we will continue with the 3 different types of color television system standard here, that is the NTSC. So this is how NTSC encoder, NTSC decoder, then PAL encoder, PAL decoder, CCAM encoder, CCAM decoder, difference between them, and the color burst. So all these parts we will see by tomorrow. So this is it for today. I wish you all the best, and just take care of yourself. Thank you.